Well, here we are at our next part of Lecture 2, Lecture 2G, and in this lecture we are going to look at colligative properties of solutions. So colligative properties may be something that you have witnessed, but maybe you're not completely familiar with. Now, for colligative properties, these are effects in a solution that are caused by the number of dissolved solute particles, but it's only determined by the number of solute particles and not the identity of the solute particles. So it doesn't matter what type of particles they are, whether it's a sugar molecule or a sodium ion. They're all just one particle. And so the effects of that they have on the colligative properties of the solution are independent of what that particle is. Now, we're going to primarily focus on non-volatile solutes, mainly because if you have a volatile solute, you have a changing concentration of something dissolved in a solution. If it's volatile, it means it's going to be leaving that solution and the concentration will be changing. So we're focusing on non-volatile solutes. And the effects that we're going to be looking at are vapor pressure, its effect on the vapor pressure of the solution, the boiling point of the solution, the freezing point of the solution, and the osmotic pressure of that solution. The effect on the solvent is in direct proportion to the concentration of the solute particles. So the more solute particles you put in, the larger effect that you're going to have. So the first one we want to take a look at refers to Raoult's law. And this is in reference to vapor pressure lowering. And a lot of these colligative properties have a directionality to them. So we say that colligative properties affect vapor pressure and specifically vapor pressure lowering. There is no colligative property of vapor pressure raising, only lowering. And so anytime we add a solute to a solution, we always lower the vapor pressure, and that's the only direction that it moves in. So what Raoult's law says is that the vapor pressure of the solution, so that's our P solution here, so vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of pure solvent. So that's what that P0 means, is pure solvent. Now, this holds true for ideal solutions. When you have an ideal solution, it means you have a dilute solution. If you make it too concentrated, then it's no longer ideal and you start getting interactions that no longer adhere to the equation of Raoult's law. Now, if we look at changes in vapor pressure and how this takes place, well, we know that vapor pressure is caused by the evaporation of some molecules from a liquid and turns into a gas phase. That must take place at the surface. That's the only place that you can have molecules leaving a sample of liquid. So they leave from the surface. If you add a non-volatile solute, they are going to spread out throughout that solvent, become a solution, become equally distributed, and that includes at the surface of that solvent. And so there's now not as many spaces on the surface of the solvent for solvent molecules to evaporate from. And so if, let's say, you have a solution that is 10% solute particles, well, they're going to occupy 10% of the surface area, and you're going to have 10% less space for solvent molecules to evaporate from. So you would expect your vapor pressure to be 10% less. And here's just a diagram of that. So this is pure solvent. I apologize for the quality of this diagram. Pure solvent, you have molecules coming off of the surface. You have molecules coming back down onto the surface at some rate. If we come over here, where we have a non-volatile solute dissolved in here, what we see is that several of the locations on the surface of this liquid are blocked by these non-volatile solutes. And so at these locations, you can have no solvent molecules evaporating, and that lessens the vapor pressure. We can also express the equation as a change in the vapor pressure if we want to include the mole fraction of the solute. That first equation I showed you used only the solvent, and here we're going to include the mole fraction of the solute. And so what we're going to say is that we have a change in the vapor pressure of the solvent is going to be negative x solute or chi solute, so the mole fraction of the solute times the vapor pressure of pure solvent. Either of those equations will get you to the same place. It just depends on the data you're given and how you want to go about finding the vapor pressure of your solution. Now, we can deviate from Raoult's law if you start going outside of an ideal solution. And this is based on strong solute-solvent interactions. If you have an ideal solution, you can see everything is nice and linear. Vapor pressure of pure A, pure B. This would be primarily for two liquids that come together. If you start looking at strong solute-solvent interactions, you can see that the vapor pressure is significantly lowered because of the strong interaction between the two substances, A and B. The vapor pressure here is a little higher than expected if you have very weak solute-solvent interactions. And so what we try to do here, however, is try to keep everything very dilute so that we remain in an ideal solution and we get these nice linear fits. So let's take a look at an example of an equation. So we have a solution that has 1 mole of glucose, 15 moles of water. We're at 25 degrees Celsius. If we look at pure water at 25 degrees Celsius, we see that the vapor pressure is 31.68 millibar. And we want to know what is the vapor pressure of the solution of the glucose and the water together. Well, let's write down what we know. We know that we want the vapor pressure of the solution. So the vapor pressure of the solution is equal to X solvent. So this is our mole fraction of the solvent times our vapor pressure of pure solvent. So that was the first equation that we had seen. We know that our mole fraction of the solvent is going to be number of moles of the solvent, so 15 moles, over the total number of moles, so 15 from the solvent, 1 from the solute, so we get a total of 16, so we have 15 over 16, and we get a mole fraction of 0.938 for the water. So that's the water's mole fraction, 0.938. We can then just plug in our 0.938 for our mole fraction of solvent. So we have 0.938 times 31.68 millibar, and we get 29.72 millibar. Very straightforward calculations. So that becomes our new vapor pressure for our solution. Let's look at boiling point elevation. And again, we see that we named boiling point as a colligative property, and it also has a directionality. It's an elevation. Anytime you add a non-volatile solute to a solution, you will always raise its boiling point. You can never lower it. Okay, it will always go up. And this is really due to vapor pressure lowering. We're going to see a graph here in just a little bit that indicates why that takes place. But boiling point elevation is a direct result of vapor pressure lowering. Now, the equation for boiling point elevation, again, is also very straightforward. We have the change in the boiling point, so delta TB, so the B is for boiling, is equal to KB. Now, this is a boiling point constant. The B indicates it's for boiling. It is solvent specific, so water has a boiling point constant, acetone has a boiling point constant, methanol has a boiling point constant. They're all different. Okay, and then we need to look at the molarity of the solution. I'm sorry, molality of the solution, not molarity. Molality of the solution, our little m there. So here's the graph I was mentioning just a little bit ago. We see that in red we have a solution of pure benzene. So when its vapor pressure reaches an atmosphere of pressure, so 760 millimeters of torr, or millimeters of mercury, we're at 80 degrees. So at 80 degrees is where the vapor pressure of pure benzene is equal to our atmospheric pressure. So that's its boiling point, 80 degrees. Now, if I add a solute, a non-volatile solute, we know it's going to lower the vapor pressure. So at a given temperature, we see that the solution always has a lower vapor pressure. Well, what that causes to happen is as you trace that all the way up, in order to get to a vapor pressure equal to atmospheric pressure, you have to add a little bit more heat. In this case, 5.1 degrees Celsius, depending on how much material they put in. They put in 0.135. And so we have a higher boiling point here because we've lowered the vapor pressure of the solution and had to add more heat, so a higher temperature, to get that solution to boil. Let's do an example. We'll look at our glucose solution again that we did in the previous example. So we have our equation here, delta TB is equal to KBM. Something you would need to be given is the boiling point constant for water. It's equal to 0.51 degrees Celsius kilograms per mole. We know that our molality is equal to the moles of glucose over our kilograms of water. So our moles of glucose are going to be equal to 1 mole, okay, because now our molality that we're looking for is for the solute, not the solvent, like we did in the previous example. So our moles of glucose is 1 mole. Our kilograms of water, well, we know we have 15 moles of water. We have 18 grams per 1 mole. And so that'll give us the number of grams of water, and then we just need to convert to kilograms. So everything cancels out very nicely. Moles and moles cancel, grams and grams cancel. Only unit we're left with is kilograms there, and we get 0.270 kilograms. At that point, we have all the data we need. So our delta TB is equal to 0.51 degrees Celsius kilograms per mole times our molality, 1 mole of our solute per 0.270 kilograms of solvent, and that gives us 1.89 degrees Celsius. Again, we can look at our units. Our kilograms cancel here, our moles cancel here. It leaves us only with degrees Celsius, and that's the unit we want because we're looking for a temperature. Now, something to keep in mind is that we are looking for a change in temperature, or I shouldn't say looking for it, that's what we calculate. We calculate a change in the temperature. So our new boiling point is not 1.89 degrees Celsius. That's just how much we raised the boiling point by. Since the boiling point of water is normally 100 degrees Celsius, and I've raised it 1.89 degrees Celsius, my new boiling point will be 101.89 degrees Celsius. Well, let's go the other direction. Let's take a look at what happens when we try to freeze a solution. Well, we run into the freezing point colligative property, and again, this is also directional, and it's called a freezing point depression. We always lower the freezing point of a solution when we add a non-volatile solute. We never raise the freezing point, it's always lowered, it's always depressed. It works in a very similar way to vapor pressure lowering. Remember, in vapor pressure lowering, you had molecules or ions or atoms getting in the way of things evaporating from the surface. For your freezing point depression, what you get is solute particles getting in the way of crystals forming for the liquid solvent to turn into a solid. And so you end up having to lower the temperature a little bit farther in order to drive that crystallization process a little bit harder. Our equation here is pretty much identical to our boiling point elevation. The only difference is we've changed our letter to an F for freezing, so we have delta TF, so again a change in freezing point, and this is for the pure solvent, is equal to KF, so we have freezing point constant. This is different than the boiling point constant, so it's going to have a different set of values. It is also solvent specific, so you have to look at what solvent you have, go to a table and find its freezing point constant. And again, we are still using the molality of the solution. So let's go back to our glucose solution here. We have our same or close to same equation that we had earlier. Delta TF is equal to KFM. Our freezing point constant for water is 1.86 degrees Celsius per Kelvin mole. Sorry. Our freezing point constant is 1.86 degrees Celsius kilogram per mole. Our molality, of course, is the molality of the solution. So we have moles of glucose per kilograms of water. We find the kilograms of water just like we did in that previous calculation. Plug everything in. We have a delta TF, 1.86 times 1 mole over 0.270 kilograms. And now we get a freezing point depression of 6.89 degrees Celsius. Now, the same thing holds here with our calculation. This is a change in the freezing point, not the new freezing point. The normal freezing point for pure water is 0. Because it's a depression, we have to subtract the change. So 0 minus 6.89 degrees Celsius is going to give us negative 6.89 degrees Celsius. Something you have to be aware of is if you use a solvent different from water. It's easy to get into the habit of always just looking at the delta TF, put a minus sign on it, and saying that's the new freezing point because you're so used to using aqueous solutions. If you're using a solvent that is not water, it's going to have a different freezing point for the pure solvent, and so you're going to have to subtract your freezing point depression from a different number other than 0. So it's just a matter of just keeping focused and making sure you understand what you have for your solvent.